Alright, so I'm going to use the practice final to go over the review for the class. And I'll go over the main topics as I cover the different problems. That way you also have the solution to a practice exam, because you'll probably ask for it anyways. Alright, so the first one is a Castigliano's problem. We want to determine the deflection at point A due to a point load P and the distributed load W. So to do that, I'm going to use Castigliano's. The main concept from Castigliano's is that I can calculate the deflection at any point, in this case A, if I have the total energy and I do a partial derivative of that energy with respect to the load at A. Okay, if there isn't a load, you create a dummy load that we called Q in our examples, and there's plenty of examples like that. If you haven't checked the practice exam for the night exam or the night exam itself and the solution, so 2 independent videos, there's examples on how to do that. And basically all you have to do every time you have a point load is split your integral. So just as an example, if you had another load here and another load here, F2, F3, you would do an integral from A to here, because you can write this as a function of W and P, and then from here to here, or to A, I'm sorry, because you would be able to write the equation from here to here as a function. Again, every time you have a point load, your function mathematically has discontinuity, so you have to split the integral so that you can actually model your whole the full loads with a different mathematical function. Okay, so I'm gonna forget that. To solve for these, we don't need those. But again, there's plenty of examples, Castigliano's in the homeworks and the exams and everything. So let's go back to this. I want my energy, and I see that the energy that it's going to be inside this bent cantilever is due to bending. So this would just be m squared over 2ei, and then of course if I do the partial derivative with respect to the force, I'm gonna end up with m ei dm dp in this case, right? Yeah, so like I mentioned, we don't need a dummy load because we actually want the deflection at A where there is already a load. If there weren't a load there, I would have to create a dummy load. If I want the deflection somewhere over here, I would need a dummy load. And that goes for anything. Like you can have, I don't know, a beam like this with some simply supported or something, and you want the deflection here, and you don't have a force there, then you create a dummy load. Okay. Again, there's plenty of examples about that in previous exams and homework solutions and quiz solutions. So going back to this problem, well, I want to calculate that deflection at A, delta A or YA, whatever, is from 0 to L m over EI dm dp dx. Okay, where if I do a cut here anywhere between A and B, I would see this load P, this distributed load W, and an internal momentum. So when I do a sum of forces of M at this point, I would have M plus P. This distance from here to here would be X, random variable X. Okay, X. Plus the distributed load would be W times X, and it's concentrated at the middle of the centroid, which is X over 2. Okay, and this has to be equal to 0. So it means that M is minus Px minus Wx squared over 2, and dm dp, which is what I need for my integral, is minus x. Okay, this would be 0 for the second term. For the first term, it would be partial derivative with respect to p minus x. So I go back to my integral, and this is 0 to L of px squared plus wx cubed over 2. There's 1 over ei outside the integral because that's constant, and dx. I do the integral, and this is px cubed over 3 plus wx to the 4th over 4, and there was already a 2. There's an 8. Again, 1 over ei times this, evaluated an L and 0, meaning 1 over ei pl cubed over 3 plus wl to the 4th over 8. Right? I have 5 meganewton meter squared for ei, so this is 1 over 5 million, and the load is 6,000, the length is 2 meters, the distributed load is 4,000 per meter, the length is 2 meters again, and this gives me a deflection which is equal to 0.0048, and this is metric, so this is meters, or 4.8 millimeters. Done. Second one, round cantilever bar is subjected to torsion plus a transverse load. So I have P and torque. The bar is made of a ductile material having a yield strength of 50,000 psi, and we have the values for P, for the torque, and the length. Transverse shear can be neglected, so we're not going to do a VQ over IT. Determine the minimum diameter to avoid yielding using both MSS and DT criteria, maximum shearing stress and distortion energy. Okay, and I have my, so it's pointed out, not in the problem statement, but it's here, element, that's the highest stress that I'm going to get. So at that point, I'm going to have at maximum normal stress in tension from the bending. Okay, so that bending is due to the my over I, which I know for a rod is always 32 m over pi d cubed. We've done that 1,000 times, and then in this case, the moment is just the force times the length. Okay, sorry, this was a P. I'm gonna call it P times L, and then tau is the TC over J. Again, we've done this 1,000 times for rods, so this ends up being a 16T over T over pi d cubed. And in this case, it's just that because T was given. Right? So basically, if I draw that tiny element where this is the x-axis, I would have a sigma x, no sigma y, and a torsion. It goes like this, tau xy. Okay, and I can combine those two and for more circle and get my principal stresses A and B. Okay, so it's gonna be the sigma x plus sigma y over 2, basically just sigma x over 2, plus or minus the radius, which is square root of sigma x minus sigma y over 2, basically the same thing, squared, plus tau xy squared. Okay, I can factor out a 16 over pi d cubed, factor of PL plus or minus square root of PL squared T squared. Okay, and with the numbers, I have something like 500 times 5, and then same thing, 500 times 5 squared plus 1,000 squared. Going by these numbers, 1,000 for the torque and the 500 by 5 long for the moment. And so what I get from that is a Moore circle. I work out the numbers. I have my sigmas, my taus. One of them is going to be positive, the other one is going to be negative. So I know it's going to look something like this. Okay, and I am drawing it like this because I know this value is not that high. I already worked out those. So sigma A, which is sigma 1, is 26,450 over d cubed. In terms of d cubed, because I don't have d, that's what I want to find. And then this sigma B, or sigma 3, would be minus 981 over d3. Okay, why is that 3? Because this is 2 equal to 0. Basically, if I did my 3D Moore circle with the other circles here, this is what I would get, right? And then that's what I'm going to use for the two criteria. So MSS is the first one. What I'm going to do is compare I'm not erasing. Okay. For MSS, I want to compare the yield over 2. So the yield strength 50 KSI. SY is 50 KSI, meaning that the shearing yield strength is half of that, 25 KSI. And I'm going to compare this maximum shearing stress to that. Okay, so how do I get that T max from the Moore circle? I grab sigma 1 minus sigma 3 divided by 2. Diameter divided by 2 would give me the radius. Okay, or just this radius with the 16 and the pi d cubed. Whatever way you want to do it, that is going to be 13, 7, 15 d to the 3. Okay, and I also want a factor of safety of 2. So basically, I want my tau max to be not 25 but 12.5. Okay, if n is equal to SSY over tau max, which is my factor of safety, and that has to be equal to 2, that means that 2 tau max is equal to SSY, or that tau has to be half of FSY. Okay, so instead of 25, I need a 12.5. So I do that, and oh god, and the diameter is equal to, or has to be greater than 1.031 inches. Right? And then for the other one, which is distortion energy, basically all I'm going to do is compare that 50 KSI to my von Mises stress. Okay, that's why I wrote it in both ways, sigma A and sigma 1, and I'll go back to that in just a second for a review. For von Mises, I'm going to have a sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared, blah blah blah. Okay, divided by 2, and you know, like that equation. When I do this, I'm comparing it directly to SSY. To SY. Let me erase this, which is the 50 KSI. And then I do the same thing. I want my sigma prime to be, my von Mises stress to be half of sigma y, because I have that same factor of safety equal to 2. Okay, so if that is 2, then 2 sigma y, sigma prime is equal to sy, right? And when I do that, I solve for d, I get 1.025 inches, right? So let me go back for a second and explain the different failure criteria as a review. So we have two ways of looking at that. In general, when you do a Moore circle, you have 3 different cases. When both sigma A and sigma B are positive, okay? When one of them is positive and the other one is negative, B okay, and when both are negative. Okay, and this is enough to understand what we're doing. A and B, it doesn't matter which one is A and B, but let's keep it consistent. If I'm doing MSS, which is just compare this value tau max and tau max to half SSY, okay, tau max versus half of SY, okay, which is what we're calling SSY, the shearing yield strength. If I'm doing that, and you know that this is in reality a 3D Moore circle, for case 1 and 3, I would have a sigma 0, a sigma 3 equal to 0 here, and a sigma 1 equal to 0 here, right? So the maximum stress, this would be the maximum shearing stress in plane shearing stress, okay? But there's an overall circle that encompasses both of these, okay? And this tau max, overall tau max, is what I want to compare, okay? So it's not this one, and it's not this one right here. It would be a higher one, okay? How do you get that? In these cases, you're only comparing sigma A. You don't care where B is. B could have been here or here or here, wherever, different circle. The overall circle in blue, say, is what I'm going to compare to get my tau max, okay? And the way to do that is just getting sigma A minus 0 to get the diameter, and then divide by 2, okay? So in those two cases, in this case sigma B divided by 2 is what I would be comparing to SSY, okay? And when I go into this middle one, is what I just did. I would have some smaller circles inside. I am looking at this value, okay, for the tau max. So if I'm looking at that value, that's just going to be sigma A minus sigma B, which would be the diameter of the circle, and divided by 2 to get the radius, to get that tau max, okay, versus SSY. So by looking at these three cases is when we put them together, okay, in those diagrams that have sigma A and sigma B and their axes. Okay, so MMS, which is what we're looking at, we're just comparing either sigma B or sigma A if both of them are positive, okay? Quadrant 1, where sigma A is positive because it's towards the right of the 0, and sigma B is also positive because it's towards, like, upwards from the 0, okay? That would be case 1. And then all I'm doing is comparing either sigma A or sigma B, okay? See, case 1 or case 3 doesn't really matter, okay? Which is coincidentally not because they match quadrant 1 and quadrant 3, okay? Where this value is y, okay? If I'm comparing sigma A divided by 2 versus SSY, which we already said is SY over 2, I'm literally just comparing sigma A versus SY, okay? Same here, sigma B versus SY, right? So that's why I have an SY here. But then in the middle, where sigma A or sigma B are halfway there, one of them is positive and one of them is negative, okay? So for example, in quadrant 2, I have a negative sigma A, right, but a positive sigma B. And in quadrant 4, I have a positive sigma A but a negative sigma B, okay? And it doesn't matter which one is A and B. You can label them either way. If there was a rule for them, we would just have half of this, so either in that direction or in this direction, but it doesn't matter. A or B could be anything. That's why it's both positive and negative, and we have the 4 quadrants, right? In that case, all we're doing is just this straight line. That straight line, we've done it 1,000 times in class. Just mx plus b, the y-intercept, the slope. So for example, the slope here would be sigma b over sigma a, or not really, because in this case we're only looking at these values, which is sy, and this is minus sy, right? So it would be and sy over sy, which is and positive because it's a positive slope, so m is just a 1, and x is sigma a, and delta and y-intercept is sy. So you solve for that, and y is sigma b, and you end up just comparing these two, and that's why we can represent those cases as these diagrams, sigma a and sigma b, right? So we would be able to do the same thing for distortion energy. I'm not going to go over all the other 6 or the other 5 failure criteria, but just as a reminder, we would have distortion energy something like this, for dE, and we have von Mises, and we have that equation for the von Mises stress, and the other one is when we have an sy under tension, so tension, and then an SC under compression, which is a different value. Okay, it's just going to look like this. And of course this line, this y mx plus b, will change because m is no longer 1. N would be tension and compression, so st over sc as my slope. Okay, and then my y-intercept, which is the b of that equation, would be st, right? And then you solve for that, and you can find the equation for this line. Basically, all you want to do for these 3 cases, this is for ductile materials, is that your stress state, you do your sigma a and your sigma b, to be within this geometry. Okay, you want to be here, here, here. As soon as you go out of this geometry, no matter in which quadrant you are, the material is going to fail. Right? Again, there's plenty of examples here. There's homework. There are some quiz solutions that go over this. The night exam had this, so you can look at that solution if you still have questions about this. Right? Okay, so that was problem number 2. 3. In a wheel suspension of a car, the spring motion is provided by torsion bar fastened to the arm on which the wheel is mounted. The torque is in the torsion bar is created by 2500 newtons. So this is a vector coming out of the page, and then there's like dimensions for everything. And the diameter of the torsion bar, so this one, is 28 millimeters. Find the stresses in the torsion bar at the bearing by using DET theory, so distortion energy. So I'm looking at the stresses here, and that's kind of the same thing we just did. My torsion stress, which is Tc over J, which is the 16T over pi d cubed, is that due to the torsion of this cylinder from here to here. Okay, what is that torque? 300 times 2500. I'm going to do it in meters, so 0.3 is that 300. Okay, and the diameter is 0.028 cubed. Sigma minus my over I, which we know is 32m over pi d cubed. It's going to be a bending, okay, which is this distance times that force. It's going to try to bend the bar, the torsion bar, and like I just said, that's just 2500 times 0.1 over pi and the same diameter. Okay, this is 174, this is 116. What do I do with those? I get my principal stresses. So sigma A and B are the sigma x and y, so literally this is just under tension or compression, doesn't matter. I'm going to have a sigma and then a tau, and the direction again doesn't matter because I'm just looking at the principal stresses. So this would be sigma x plus sigma y divided by 2 for the center, and then the radius would be same thing, minus sigma x minus sigma y, but sigma y is 0, so that's why it's the same thing, squared, plus the tau squared. Okay. So this gives me A and B. Again, it doesn't matter which one's which. 241.4 or minus 125.4 megapascals. And what do I do with those? I need, because I'm told to compare this using the distortion energy of von Mises. Okay, so I use the von Mises equation, the one that I wrote before, and I get a 322.6 megapascals. Okay, using this is sigma 1, this is sigma 3, and sigma 2 equals to 0. Okay, why? Because one is positive and the other one is negative, and we always want sigma 1 to be the highest and sigma 3 to be the lowest, right? We compare it, find the stresses in the torsion or the bearing. We don't compare it, we just wanted to find the stresses. So for distortion energy, what we want is the von Mises stress. Done. 4. An axle has a groove. An axle is ground, so that's the surface, and this is, we're not going to use it, but it's just like the surface. Like there's 4, the roughness, 7 micrometers, so that's small, but just like to see what the difference in the surface is. Okay, so it's measuring just the surface roughness, 7 micrometers. We're not going to use that. The axle is subjected to a tensile loading P, 18 plus or minus 12. The material is this material. We will use only this. We can use these other properties, but we didn't go over that in class. So we can just solve it like with everything we learned in class anyways. So I'm going to use the ultimate strength for everything. Determine a factor of safety with respect to fatigue failure if the ratio of the mean value and the amplitude of the loading stress is constant. So there's fatigue. First time we are just not just given a yield strength, but we actually have to calculate the property, in this case the endurance limit. That endurance limit, SE, will be my first approximation of SE, and then some marine factors to do some correction. I'm going to stop at C because I don't have any temperature information or reliability information. I only have SE prime, which is 1/2 of 430, so 215 megapascals. I'm going to have a KA, which is a surface, so I know it's ground. I will go to this diagram. Ground is in megapascals, this and this. Okay, I'm gonna have a KB, a size, so I'm in millimeters, and the diameter is either 26 or 30, so I am within this range, so I'm gonna use this equation. And KC is the type of loading, so in this case it's axial, so I'm gonna use 0.85. Okay, again, no temperature or reliability. So go back to this. What I just said is I'm going to use .38 SUT to the B for KB. That's for ground. KB, the size, I'm going to use 1.24, with millimeters being 26. I'm going to use the highest stress is going to happen at the groove. Okay, so I'm going to use the 26, 0.107, and KC is 0.85 because it's an axial loading. Okay, so I get these numbers, calculator, and SE from this is equal to 147 megapascals. Okay. Why am I going to use that? Because for my factor of safety, I want, depending on the criterion that I use, so let's go with Goodman so that it's the easiest for now. I'm going to have a sigma, in this case just the sigma, not the sigma prime, because it's only under tension, M compared to SUT, and sigma A compared to the endurance limit. Okay, you don't go with Goodman, but with I don't know, Morrow or Gerber or some other that uses yield strength, you would be using this instead of SUT for sigma m. And one of these terms might be squared or something like that to get the n. Okay, but I'm gonna go with Goodman since they just asked me for a factor of safety. So I'm gonna go with the easier one for now. Right? So I have SUT and I have SE. Now I need the stresses. Stresses are easy because it's just a normal stress. So it's just load over area. And since this is a cylinder, this is just 4p over pi, or not a cylinder, a rod, d squared. Okay, just replacing a by pi d squared over 4. And with this, I can get my mean stress, which would be with the mean force and the alternating force. Okay, I need, besides this, so I'm missing one thing here, to get my coefficients. So there's going to be a stress concentration coefficient. Okay, for sigma mean, I'm going to use a KT. Okay, not KS because it's not shearing, it's normal, and it's an T, not an F because it's not fatigue yet. This is mean, so this is constant. Okay, so 4p mean over pi d squared. And for sigma a, which is the alternating one, I will use kf. Okay, with p alternating pi d squared. That's it. So I'm gonna look those up. And to look those up, I need some diagrams that look. I'm not gonna actually use the diagram, but something like that looks like this. Obviously, it's not under moment, it's not under torsion, sorry. It's under a force, and of course, this is not the geometry. I would be looking for something like this. Okay, and actually, that one would be pretty close. We could probably use that. There's going to be a better one which represents exactly what I have, but if I were to use something that comes close to d over d being 1, okay, I could have the 30 and then another 30 on the other side. Okay, but again, I'm not going to use that. All I know, so I'm going to skip that, but all I know is that KT that I need here comes from the radius of the notch and the capital D for that specific KT diagram. Okay, so the KT diagram for that is going to give me a 2.6 stress concentration factor. Then I need to find a Q sensitivity so that I can transform that into a KF. I'm still going to use the 2.6 because my mean stress is constant. So I need a KT, not a KF. But I still need also the Q to get a KF for the fatigue part, which is the alternating stress here. So I go to Q diagram, not for KS because that's shearing, QS, just the regular Q, that's the normal one. And I need my SUT, which was 430, so I'm close to this line. And the notch radius is 0.5. I go here and I find that value, and that Q would be close to 0.7. Okay, and then my KF is 1 plus Q KT minus 1. So I use these two values and I get it to 0.12. Okay, so I'm gonna rewrite this with the numbers. Sigma m would be at 2.6 times 4 times 18,000, sorry, because that's my normal force here. And then the other one is going to be a 12,000. Okay, a PA alternating. So sigma A is going to be the KFS, the 2.12 that I just calculated. And then this divided by P, diameter again being the 26. We're going to do 0.026 meters squared. Same here. 0.026 meters. I can do it in millimeters, and then so the number would be just on megapascals. If I don't do it in megapascals, I would just get 88 million. That's fine. Megapascals, and then for this one, 47.92 megapascals. And then that's it, because these are the two values that I was missing here, sigma m and sigma a. So I put those there. And n for Goodman would just be 88.15, which is the m divided by my SUT, which is 430, and then a 47.92, which is the alternating, compared to my SE, which is the 147. Okay, into a -1, and that gives me a factor of safety of 1.88. Done. 5. Maybe I can do a quick review here for the different criterion. I'm just gonna do just one example of where those were coming from. So basically, for fatigue, if it's an alternating stress, you're just comparing your alternating stress to SE, your endurance limit. If it's lower than SE, you're good, and you can calculate a factor of safety as SE over sigma. Again, just an alternating, completely reversible stress. And your SN diagram, so SF, actually fatigue strength versus the number of cycles, you have something that looks like this. And this is 1,000,000 cycles, this is 1,000 cycles. You start with SUT, and then as time goes by, or the number of cycles increases, you have a fraction of your SUT here, and then from 1,000 to 1,000,000, this is described by a straight line. This is actually log of n, so a straight line in a semi-log would be described as a n to the b. Okay, this being y, this being x axis. And then a and b can be figured out because you already know these values. So you have SE when x is equal to 10 to the 6, y is equal to SE. If x is equal to 10 to the 3, y is equal to FSUT. So you grab these 2 points with this equation, and you can solve for a and b. We did that 1,000 times, and then you get your equations for A and B, literally. So FSUT squared over SE, something like this, and then minus 1/3 of log FSUT over SE. You get that from solving from this. You did that in a quiz. Again, if you forgot about that, just look at the solution. And so again, this is for completely reversible stresses, meaning that your stresses over time go up and down from a positive value to a negative value, sigma to minus sigma. Okay, and this can be a combination of torsion and sigma, normal stresses. So you can also have like a von Mises, everything is synced, the torsion and the bending and everything, and it goes up and down to the same value. That's completely reversible stresses. Okay, this goes up and down to the same value. And so if your factor of safety for infinite life, which is after this, is not over 1, it means that your stress is higher than SE. You're giving stress is somewhere over here, it means that it's going to fail at some point for a given n. And then you can solve for that n using this equation, and that's why we wanted A and B, right? But if your stress is not completely reversible, your stress is something like, it can be something like this. Okay, it's still positive and negative, but it's not the same value. This is lower than this value. Or something like this, for example, with the spring, it's always under compression, okay, or always under tension, and it's fluctuating. So those fluctuating stresses are going to have a mean value, sigma m, and an alternating stress, which is this amplitude, sigma a. Right? So the diagrams that we looked at for the different failure criteria, we're comparing my sigma m, which is constant through over time. Sigma m, we're going to compare them to, depending on the criterion, the yield strength or the ultimate strength of the true fracture strength, right? And my sigma alternating, which is what changes goes up and down over time, and that should be compared to the fatigue strength, or in this case SE. We're gonna have different lines. So the most common one was Goodman. Okay, we have others like Gerber or Acme or Morrow, and so the difference is that they're gonna use true fracture strength, or they're gonna be curved like this or like that, and so those lines are gonna be described by the different equations that we looked at. But that's basically how it works. This is why this is where those equations are coming from. Just comparing alternating stresses to fatigue strength, in this case the endurance limit, and then the constant stresses to the constant properties that we dealt with. And that's why there's going to be those two types of properties in those equations. For shafts specifically, we also had an equation for the diameter. So depending on the failure criterion that we use, there's also going to be an equation D. One more thing that we talked about when we were doing shafts is the capital A and capital B. This was just combining both torsion and sigma into a von Mises stress, and then factoring out everything that was not the mean torque, alternating torque, mean moment, and alternating moment. Okay, so these two are gonna already include things like the KF and the KFS. Okay, for the torques. So this would be alternating, moment alternating. You know, I don't remember actually the values here, but something like this. Okay, and then for the mean moment, the same thing. Right. That was just a generalization, so that you don't have to do this process every time and come up with the von Mises stress. And then there's a lot of common denominator for shafts. There's always going to be the, you know, the 16 over pi d cubed that we did several times. Okay. So that was it. This problem was much shorter than all of that explanation, but that's just as for our review. 5. It is required to design a helical compression spring of a circular wire, which will vary from 2.5 to 3.5 kilonewtons. For that range of load, the deflection of the spring should be 5 millimeters. So all they're saying is that for a changing force, a delta F of 1 kilonewton, the change of deflection should be 5 millimeters. Right? So K is just 1,000 newtons over 5 millimeters, or 200 newtons per millimeter. So I already have K. Spring index is 5. So C, which is D over D, is 5. Has a square and ground ends. Spring wire material is SUT 1050 megapascals, and G, that's known. And the permissible shear stress of the spring wire should be taken as 50%. So they're telling me that SSY is 50% of SUT. Remember that this value changes depending on the type of material that you're using. And then if SUT is not given, in this case it is. So 525 megapascals. You would use this table that depends on the diameter. So again, that same semi-log relationship between diameter and SUT. You're going to have an A D to the M for SUT. Okay, so exactly the same as my A N to the B that we just looked at.
except m in this case is a positive exponent and b is a negative exponent here. But it's literally the same thing. Right, so I already know k. If I know my maximum shearing stress, let's say, yeah, I'm not gonna, well, yeah, we can work the numbers as well. I know that my tau max should times, or like if my factor of safety is S is Y over tau max, right? I know that N times my tau max is S is Y, or that my tau max should be S is Y over N, which we usually use at least 1.2 for all springs. Okay, so I'm going to use that. So I know this value, 525 over 1.2, and I know that my tau max is equal to 8F max, maximum force, D over pi D cubed times the KB. Okay, a correction factor from that torsion stress. I could change that D over D as a C, so 8F max over pi D squared, and that KB, 4C plus 2, 4C minus 3, which is the one that we use, I already have the C. Okay, so KB would just be 4 times 5 plus 2, 22, divided by 4 times 5, 20 minus 3, 17. Okay, so I have that. And my maximum force, so this is part of my design, this is where I'm making the decision. I'm going to say that that maximum force, this is the range that I needed, 2.5 to 3.5. So I'm going to make the solid length cause that 3.5 kilonewtons. I don't want it to be able to compress even further than that, because then the stresses would go up. Okay, so I'm going to make it so that 3.5 is the maximum force, right? And basically all I'm doing here is solving for D, right? So KB, and this is equal to S is Y over N. Okay, I'm just going to leave it in terms of the variables for now. D would be equal to 8 F max C over times N over pi SSY times KB. Okay, in terms of variables so far, F max 3.5, C given 5, N I'm assuming 1.2 at least. S is Y, I already calculated the first thing that I did, and KB, because I have C, I can calculate it, and I already did 22 over 17 here, right? And that would give me D squared. So I'm going to do square root of that to get my D. So I already have the wire diameter. If I have the wire diameter, I can get the number of active coils, because if I have the spring rate, which is D to the 4th G over 8D cubed NA, I can solve for NA. D to the 4th G over 8D to the 3rd K. G was given, D I just found. Capital D would just be 5 times, right? Because I have my spring rate here, 5 times lowercase d, and K was the first thing that I found here. Okay, so I have my number of active coils. Number of total coils is 2 more than the number of active coils, because it's ground and squared and ground ends. And so my LS solid length would just be number of total coils times the diameter, which I already found. Okay, solid length, number of active coils and total coils, I just found that. Coil diameter is the capital D, which is just 5 times the wire diameter. And the free length would be from that table, I don't have it with me, but for ground, for squared and ground, there's going to be a free length. in terms of the numbers total of coils and the pitch. I'll upload the numbers. I'll upload the solution. I'll upload the number solution for this later. I didn't do it before the video, so I don't want to waste time doing those calculations. 6. A double thread Acme stub screw of known major diameter is in a jack having a plain thrust collar of known mean diameter. Coefficients of running friction are estimated as 0.1 for the collar and 0.11 for the screw. Determine the pitch, lead, depth, mean diameter, helix angle, everything. Estimate the torque to raise or lower the load. So this says for 5,000. Let's go with that. Not the one from the diagram. And if the screw is lifting that same load at a rate of 4 feet per minute, determine the screw RPM. Easy. And determine if the screw will overhaul if the ball thrust bearing of negligible friction were used in place of the plain thrust collar. Okay. So the first thing that we can do is we know the Acme profile, and we know that this is distance from here to here is the P. Extend this P over 2. Which is the P over 2. We can find all of this from A pretty easily. So one thing that you would get from a table or just by googling Acme stub screw of nominal diameter of 2 inches is that you'll find that they have 4 threads, like starting from like 1.5 if I'm not mistaken. They're gonna have 4 threads per inch. Okay, so like you just Google this and you find that out. Like when you go, depending on the diameter, you're gonna find the number of threads per inch for Acme screws. So that's the first thing that you need. Why? Because if you know that there's 4 threads per inch, it means that the pitch is 1 inch, 4 threads, each one of 0.25 inches. Right. The fact that it's a double threaded Acme stub means that if I'm looking at my screw and my thread from the front and a thread from the back, front, back, front, back, there's 2. Another thread here, thread in the back, front, back. What does that mean? That when I turn a nut or the screw a full turn, it'll actually go up 2 pitches, because the pitch is the distance from here to here. Okay, so if I know that the pitch is 1/4, the lead, which is the distance that the screw will go in or out after a full turn, would be 2 pitches. Right? And if I want the nominal the mean diameter, which is what I'm going to use in my equations, we've done this 1,000 times, but it's just the nominal diameter minus P over 4. So this would be P over 2. Sorry, I messed that up. This would be P over 4 on each side. Basically 2 times P over 4, or just this, which would be the 2 minus half of 0.25. So whatever this value is, 0.625. I think we did this already. 375. Okay, whatever that is. Okay, so I have the pitch, the lead, the thread depth would just be this, mean pitch diameter, and the helix angle. So the helix angle, it's also something that we looked at in class and in several problems. Be the lambda, so tangent of the lead, so the 2 pitches here, lead over pi d. Okay, so if I open this cylinder, thread in the front, thread in the back, and I open this cylinder as a flat piece of paper, what you would see is that it goes down a lead when it advances a circumference. Okay, so that angle lambda would be tangent of L over pi d, right? And so lambda in this case would be 4.73 degrees. Okay, estimate starting torque for raising and lowering 5,000 load. So we have, I'm gonna use this. We have an equation to lower the load, to raise the load, and it looks like this. This just comes from the basically what I just erased. There's going to be a force, and then there's going to be a normal, and there's going to be a friction, right? We did this already, and if we do the sum of forces in all directions, and then whatever the torque, simply like this and like this. Sorry. The torque, or the force FR, then if you multiply by the radius dm over 2, will give you the torque. Sum of forces in the x and y direction gives you this equation, right? Again, that's explained, I think that was in a video. Yeah, that's definitely in a video where I explained the stresses also on the threads of the screw. And so this looks like this, dm secant of alpha over pi dm minus fl secant of alpha. And to that I have to also overcome the friction of the collar. So the friction of the collar here is given by fc dc over 2. The friction of the collar, the diameter of the collar, and the same load. Okay, because that's the normal force that is generated at the collar, right? So I do that. I have my, I'm just gonna write down what I'd have. My load, my lead, friction at the thread, friction of the collar. Alpha would be a 14.5 degrees because we know that this angle is 29. Okay. And dm would be what I found before, so d minus p over 2. I put all of those in that equation and I get my TR. Okay, I also want TL. So TL would be same equation with pi f dm secant of alpha minus L in the numerator, and then pi dm plus f L secant of alpha in the denominator. Okay. The second term is just the frictions of the collar, so it doesn't matter that you're raising or lowering the load. There's always going to be that friction between the collar and your load, right? Or the screw, whatever is having the friction with the other. Okay, and again with the same values, all that's changing is just the numerator and the signs. And I would have TL. Sorry, the torque required to lower the load. If the screw is lifting a 500-pound load at a rate of 4 feet per minute, determine the screw RPM. That one is a super easy one, because if the screw thread is going up at 4 feet per minute, times 12 inch per minute, okay, and each thread will go up 0.5 inches per revolution, right? Because that's the lead. Each revolution, full revolution, will make this thread go down a lead, which is the 2 pitches, because it's double threaded, right? And you're done. 96 revs per minute. Right? That's C. And then D. Determine if the screw will overhaul if the ball thrust bearing of negligible friction. So I'm going to replace this color with a ball thrust bearing. It's just a bearing, so I'm assuming negligible friction. And And basically what I'm doing is I'm removing this term because there's no friction. Okay, but there's still friction within the thread, so the rest is that. And I'm checking if the screw will overhaul, meaning that the torque required to lower the load here, bring it down, is 0 or a negative value, meaning that just the load itself would make the screw start screwing in and go down in the downward direction. How do I know if this is 0 or negative? If this numerator is 0 or negative. So if pi f dm secant of alpha minus L is lower or equal than 0, it will overhaul. Okay, I put those values in there and I get something like 0.18 ish and positive, so it means that it's greater than 0, so it means that it's locked into place. It means that the load, it means that the load, oh,